mass flow rate. You are here already at the maximum TIT. You are at everything maximum. So how can you reach 100% more, so an increase, doubling the takeoff thrust? There is only one way. This is to increase m dot. But if you increase m dot, what is the danger? The danger would be that in the A throat, you could reach m throat is equal to 1, because you need to increase the m dot by a factor 2. And increasing the m dot of a factor 2, that means you increase the throat Mach number by a factor 2, and then you could reach indeed 1. And that's this what we call choking of the intake. Choking of the intake. And how will we solve that? How will we solve that? We will solve that in 2 steps. The first thing that we will do, during the design, the designer will select a maximum design Mach number of m throat. How and why? It is in order to avoid to have too many losses like these ones. These ones are related to a local effect. But this local effect will increase if the Mach throat will increase. And so we will take a very large margin compared to 1, maybe 0.6, 0.62, 0.64, something like that. So far away from 1, but also not too small. Otherwise, we could have, let's say, problems of being able to have a sufficient flow rate arriving at the level of the compressor. We would have to increase too much A throat, and that would give a too large intake and too much, let's say, cross-section for the cross-section of the aircraft. So maybe we could be up to 0.65, something like that. But so not high, but not too small, otherwise the intake is becoming enormous. But you see that if you take 0.65, how can you increase the thrust, so the mass flow rate, so the m throat by a factor 2? This is impossible, because if you increase that by a factor 2, you have 1.3, and we can pass only with 1. So it's impossible. So you see that you have to solve the problem in 2 steps. Choosing a throat, Mach design, and you need to put extra doors. Extra doors. So these extra doors will be open only in exceptional circumstances. Exceptional circumstances. So if you take the Harrier or the AV-8B that you have on the aircraft carriers of the Americans, so they are not always taking off vertically. Sometimes they are taking off on the ramp, if they are taking off from an aircraft carrier, or if they are taking off from a normal runway, they are taking off horizontally. Sometimes they are taking off and landing vertically, then at that time they will open the extra doors that you have there. So this is something that you can have, so additional ports in order to be able to take off vertically. It's also the same with the GSF. The GSF is also having some variable geometry that is used at the moment of the takeoff when you have the vertical takeoff version of the system. And related to that, I can also certainly say that in something that I've explained before, you have some solutions that I will, of course, there are a lot of solutions, but in something, a first particular solution that I can explain, it would be to have the lower lip here that can be tilted down. If you can tilt the lower lip down, you see that the flow is entering without having this turbulence. So you have the lip that is like this, and when you are taking off or landing, when you are at high angle of attack, you put the lip down. This is, for example, like this on the Eurofighter. There are two small lips that are going down. This is also like this on the F-15. On the side intake, the side intake is going down like this when you are in this high angle of attack configuration. And related to this case, for example, you have some aircraft that are closing their intake. They close the intake. They put a door here because it's too dangerous. And of course, at this moment, they need to open an extra door that is here. I'm mentioning that because it's not intended for vertical takeoff. It has nothing to see with what I have just explained here. It has nothing to see with what I have just explained there. It's just in order to protect the engine, you close the intake like this. The bolts or the tree branch, I don't know, cannot fly inside, and you open an intake there on the top. This is, for example, the case on the MiG-29. MiG-29, the Russians, they have always implemented, let's say, rather strange solutions on their aircraft because they have very bad weather conditions and they have runways that are everywhere in the nose or in Siberia and so on, and with very difficult weather conditions, a lot of salt also on the runways in order to de-ice the runway, and so in the winter they have very bad weather conditions for the engines. Also, and this will be the final, let's say, example I will give, what you could do, this is in the intake, let's say you have an intake like this, you can have also a grid that is lowered down like this. If you have a danger of stones, branches, or bad conditions on the runway. And you have then a kind of filter, and this is something, a grid, like this, like a filter that will stop everything. Something that you cannot use in flight, of course, because it's delivering a much too low ram recovery. The ram recovery you have with this is much, much too low in flight. But at takeoff, this is not so important. You use the afterburning, and this is on the Sukhoi 27 that you have that, on the flanker, and this is not a problem because you have afterburning. The danger, of course, is that you could have icing here. You could have icing on the filter, on the grid that you are putting on the course grid that you have there. So you see that takeoff is not an easy condition. And we have already discussed that a lot. We had discussed that related to hot and high humid. This is the combination of three very bad conditions. And you see that you combine even worse conditions due to the fact that we have high mass flow rate. So that means that the ram recovery will be lower. We have a low Mach number. Again, the ram recovery will be lower. If you have a low temperature, icing danger, and so on, and so on, and so on. And very often, the manufacturers, they have been forced to find, in fact, very special solutions in order to solve these problems of the low Mach number at takeoff. Okay? In fact, when discussing all this, it's very interesting, but we are forgetting something that is maybe as important as what we have until now discussed for the intake. So, if you look at everything that we have discussed about the intake, we have discussed, I take a civil intake. Short one. Symmetric one. So with A1 here, okay? And I take the cruise conditions. I say I solve the problems of takeoff. Takeoff in civil aircraft, this is just 1% of the flight time, even maybe less, so this is solved. And I have the parallel flow here. I have this situation with here the section AA, here the section AI, here the throat, and here the section A1, okay? And everything I have discussed until now was related to the RAM recovery. And the RAM recovery, we know it's linked with the physical intake. The RAM recovery in the non-physical intake is, let's say, equal to 1. We have said that PTI is equal to PTA. So in the non-physical intake, there is no loss of total pressure, and the RAM recovery is just equal to PT1 divided by PTI, and PTI is equal to PTA. Okay? This is what we can call the study of the internal flow. So we are, let's say, inside the intake. But when doing that, we forget, in fact, something. What do we forget? This is the following. Something that you cannot, in fact, discover by yourself with what I have explained until now, but that you will understand very clearly from now on. So here we have the compressor. So the compressor, this is something like this. So compressor is something like this with a combustion chamber. Here we have a turbine. I take a very short turbine, and here I have the exhaust nozzle. And I have, let's say, the external wall that is continuing here up to the exhaust nozzle, and here I have my section A5, and I have here my V-jet that I have, and normally here P5 is equal to PA in the best case, let's say, or not equal to PA in some other circumstances. And you remember that I have given you, without demonstrating that, I have given you the equation of the thrust, and the equation of the thrust was F is equal to m dot multiplied by V jet minus VA plus A5 P5 minus PA. You remember that it was the result of some approximation, because the first equation that I had given you was m dot plus m dot F multiplied by V jet minus m dot multiplied by VA plus A5 P5 minus PA. An equation that I have not yet demonstrated, but I will demonstrate it tomorrow. But I am explaining you what is the problem due to this equation. In fact, this equation